Alright, hi everyone. Can everybody hear this okay? Is it like super loud? No? Okay, let me know if this like blows your ears off or if sounds like I'm eating the mic. Just tell me to move it around. Okay, hi everyone. Welcome to Lecture 1 for CS61BL Summer 2019. Woo! Alright, thank you all for coming. So we have a fun lecture packed for you today. We'll start off with some announcements and then we'll just dive right into everything. So announcements, remember that there is a pre-semester survey that we send out to you. It's due this Friday at 11:59 p.m. if you would like to get 1 extra credit point. So you'll find that on Piazza. It's in the welcome post. So just click there, fill out the survey, and then you'll get that. Then you will, get that 1 point of extra credit. So just remember to fill that out. Easy extra credit right there. The next thing is that there's a project, Project Zero, just released, I believe like a few days ago. So it will be due this Saturday at 11:59 p.m. Autograder will be released on Thursday, but we will also be having a project party coming up. It's slated for this Friday, but we'll let you know what the exact details are in the Piazza post later on. So just if you want a place to work on it, if you need some more help, we'll have a project party there for you. All right, so instructor office hours will begin tomorrow. So the locations and time, or the time is listed here. It's Monday, Thursday from 10 to 11 a.m., Tuesday, Friday from 4 to 5 p.m. And I didn't put the location here, but it's going to be in 283E Soda. So downstairs, next to 277, there's going to be those little alcoves, and the office hours will be there. So if you can't make it for whatever reason, you still like to talk to us about something, just send us an email, and then we can coordinate and set up an appointment with you directly. All right? And if you have any questions that we are unable to get to, just post on this live lecture thread right here. It's pinned at the top, so if you have any questions, let us know. And then one of our TAs or one of the instructors who are sitting on standby will be able to help you with that. All right? Okay, any questions? Perfect. All right, so let's begin. So first off, let's just introduce what this whole class is about. So what is it about? There's a few things, but it's titled Data Structures and Algorithms for the most part. And the reason why is we want to teach you efficiency. If you've taken another programming course before, you probably learned maybe how to code like recursion in, let's say, the Fibonacci example. But we want to be able to teach you ways to write your code more efficiently. So one, the thing that you want to do will run a lot faster. But another thing is that the amount of time that you spend on writing this code will be a lot faster too. If you know what data structures to use, what algorithms to use, those will already mostly be there for you, so you don't have to reinvent the wheel. So we're trying to create a more efficient program so it'll run faster. We also want to create a more efficient you, so then you won't have to spend so much time copying and pasting code here and there to get something to work. All right, the other thing that we focus on is programming. So we want you to be able to design, build, test, and debug super, super large programs. So you probably haven't seen it yet, but as we dive later and later into this semester, you'll be working on really, really huge projects with a bunch of other people, and this is supposed to get you kind of oriented to what it's like in the real world, where you're going to be working on a team with a bunch of other people that you may or may not like, and you'll be creating this giant project together. So that's the point of this, this class, is to help get you familiar with this idea, as well as to introduce you to a lot of programming tools that are very useful for this class, but also in the real world as well. So you've already seen Git. Maybe you love it, maybe you hate it. Well, we'll see what your relationship looks like as you progress through the semester, but Git is one of them. We'll have an IDE, which is, we'll be using IntelliJ this semester. It's basically like a fancy text editor that will help you be super lazy, and command line and a bunch of other different things. So programming tools, and most of all, you'll be writing a bunch of Java. This is not the focus of the course, but know that a lot of industry tends to use Java or Java-like languages, so it'll kind of get you familiar with what is basically going to be out there in the world when you maybe start an industry or get a job somewhere else. All right, so we'll assume that you have a solid foundation in the programming fundamentals, so object-oriented programming, recursion, lists, and trees. So if you don't really remember, that's totally okay, but if you have taken something like 61A or an intro programming class already, then you should have seen some of these things already. Okay? All right. So why do we want to study data structures and algorithms anyway? Right? These data structures and algorithms actually have like a very, very tight-knit relationship with our everyday lives. So let's just say Google, for example. Google, you can type something into the search bar and get something to show up for you. So something like this, why is G? We get a lot of different options, including why is Git so confusing? So that's one of the things that you'll see, but we can see it actually happen live. So let's open up google.com. Right, in this search bar here, you can type whatever you want, and it'll autocomplete stuff for you. So like, why is Bitcoin going up? Why is Bitcoin rising? Why is IQ banned? Why is Office leaving Netflix? You get a whole bunch of different things based on your recommendations. This is incognito, by the way, so don't worry, like, maybe they searched something weird, but don't worry, this is incognito. You can search like, why is Christine evil? I don't know. What did I do to become evil? Who knows? Why is Jackson WY so expensive? Why is Jackson Pollock so important? And then we can see one for Matt. Why is Matt balling so fast? Who knows what that means? All right, so you can see that it autocompletes very, very fast. And the data structure that they're probably using, which you will actually be implementing in this class, is what is known as a trie. So you don't have to worry about what that is yet, but you will be able to actually implement something like this that will help you autocomplete in basically record time. There's probably terabytes of data behind this trying to provide suggestions for you, but it does it like in a snap of a finger. So it's really cool what you can do with data structures and algorithms. Right, so that's one thing. Another thing is that they're a major driver of potentially progress in society. So one of the really cool things that has been happening recently with machine learning especially is this thing called AlphaGo. So Go is a game that we humans thought like computers could never play, but through the DeepMind, which is like a company owned by Google, they have developed this AlphaGo kind of program that will basically play Go really, really well. And it actually beat one of the reigning world champions of Go, and this is what he had to say about it. Is that after humanity spent thousands of years improving tactics, computers tell us that humans are completely wrong. I would go as far as to say that not a single human has touched the edge of truth of Go. So computers are becoming super, I guess, like very good at playing these turn-based games, but through this we can see that there's a lot of way for AI to go and machine learning to go in general. Another thing is that there's this new fad of self-driving cars. They're not really here yet, but self-driving cars is going to be a huge change. Like, it's going to really affect how we see everyday life if they ever get really slated and introduced into the world as a regularity. Right? There's a lot of people who maybe die in car crashes every day. Self-driving cars can help with that. There's a lot of traffic that can be fixed, and self-driving cars can be more efficient about how the cars move around each other and improve traffic. Another maybe downside of this is that a lot of jobs actually rely on driving. So like, for example, truck deliveries, Uber, Lyft, all those different types of driving is going to be essentially removed once these self-driving cars come into the society. So you got to think about why, like, if this introduction is going to be progress, hopefully it is, but there's essentially going to be a lot of different things that we'll see coming up in the future related to computer science in general. All right, another thing is that maybe you don't want to like try to change the world. Maybe you just want to become a better programmer. So this is a quote from Linus Torvalds. He's the creator of Linux. So if you use a Linux machine like Ubuntu or Arch Linux, he's the creator of that. He also created Git, so you're welcome. But this is what he said about data structures. So the difference between a bad programmer and a good one is whether the programmer considers code or data structures more important. Bad programmers worry about the code. Good programmers worry about data structures and their relationships. So something from the creator of Linux and Git, he said something like this. So this further shows how data structures can be super important into creating good programs and becoming a good programmer yourself. So keep this in mind as you're going through the class. If you ever hate Git, just think about this and you'll remember that data structures are good. Okay, another thing is just to understand the universe better. So a lot of inventions or scientific findings today is not finding like a new formula that describes the world, but it's really just trying to see the universe in a different way or trying to have a better idea of what the universe looks like. So I don't know if you guys have seen this, but what's on the left is the first image of a black hole. And what we were able to get this image, not we, but like the people who made it, but those people were able to get this image through computer science algorithms. They basically took all the data from the Event Horizon telescopes, which is just scattered telescopes around the world, and try to combine them in the most reasonable way. So they used an algorithm to take all that data and try to formulate something that would look similar to what we think of a black hole, but try not to include too much bias in what we already believe a black hole looks like. So that's really cool. Another thing is this simulation of a galaxy forming. So this is all a simulation. It's not like someone went in with a video camera and like took a video of how a galaxy formed. But you can see that this simulation is kind of slow, but this is not like actual footage. This is somebody who coded this up and made a simulation of a galaxy forming. So a lot of cool stuff, and a lot of cool stuff to come as well. Okay, so another reason why is maybe just you want to create really cool looking stuff. So here, I'll just play this video. Let's see if it's, oh God, okay. So fair warning, the music is very, very loud, so maybe you want to cover your ears a bit, but I think it's good background music for this. Okay, I hope that wasn't too jarring, but these are fluid simulations with really cool background music. But these fluid simulations are not like video recordings of how fluid behaves. And someone had to code up this behavior of how a fluid works. And similarly, this is another one here. I'm pretty sure it has also very loud music, so I'm not going to play it. But you can look at it on your own time as well. But they make a lot of cool things that really, really represent like what happens in the real world. So really cool things. Okay, and another one, maybe like a more theoretical example, is just to solve or stimulating mathematical and theoretical problems. So I don't know how many of you guys have tried to draw this house before. How many of you guys have tried this challenge before? Yeah, a few of you? You basically have to draw this house without picking up your pencil or going back over lines that you've created. All right, so that's one problem. You can probably bang your head over and figure out how to draw this house. But another semi-related problem is the 7 bridges of Königsberg. So these bridges, they are set up in a way where you actually cannot pass over every bridge once without crossing over one again. So if you try hard enough, you really won't, like this one's actually impossible. You can't actually do the correct series of steps to get through all the bridges. And these do seem like very separate like fields or very separate concepts from each other, but we can actually relate them together with what is called a graph. So later in this class, you'll be learning about what a graph is, and this is the graph representation of the 7 bridges of Königsberg. The graph representation for this one will look a little bit different, but you'll see how just the difference in how the graph representations look make one problem possible to solve, while the other impossible to solve. Okay, and maybe the last one is just everybody else is doing it. So here is the enrollment for CS61B over the past 20-ish years. So this was right after the dot-com boom. So this is dot-com boom right here. And you can see that the enrollment was pretty low, 200, 300 at most. But once we started getting into recent history, you could see that this number just jumped, skyrocketed. So this past spring, we had around 1,600 students with a whole bunch of people on the wait list. And this is probably going to keep going up and up and up. So maybe you're doing it because everybody else is doing it, and that's totally okay. It's what's new, what's cool, and that's totally fine. Okay, so before we get into more of the course policy stuff, I'd like to introduce ourselves first. So here's a giant picture of me. So I'm Christine. I normally wear glasses, but here I'm not. I just graduated from Berkeley, 2019 computer science, woo! This is actually my 8th time teaching this class, so I really, really like this class, as you can see by that number. But yeah, you're in for a treat. This is a really, really great class. Technical interests are, I like doing software engineering, big projects, and systems-related things. Actual interests, I really like camping, backpacking, playing games, and just music-related stuff. Fun fact, I have a twin sister. She goes to Berkeley, and she's actually taking summer classes, so if you see somebody who looks like me, and you wave and you don't get a response, it's not me trying to ignore you. I'm actually really good with like faces and names, so definitely say hi. She'll, like, don't worry if you're not going to get a response or anything, but just just know that this is the case. Like, I promise I'll wave back to you if I see you, but if not, this is the reason why. Okay, I promise I'm not ignoring you. All right, let's have the other instructors come up and then introduce themselves really quickly. Yeah, next slide.
All right, hi, I'm Jackson. You can see I'm also graduating in 2019, but not in the spring because I have an extra major and it takes a while. So I'm computer science, cognitive science, data science. You can talk to me about any of those if you're interested. I've been teaching for a little while. One time I worked at JPL, which was cool because those are my initials, and I put that in my application, and it worked. Technical interests, I forgot to fill them out, but technically I like CS. Actual interests, I like Jugger, which is this weird game, and then board games, video games are fun too. Fun fact, I have a set of movie quality Stormtrooper armor. But yeah, that's cool, I guess. Next.
Hello everyone, my name is Matt. I'm one of the other instructors. I graduated last spring in EECS and also with a minor in bioengineering. This is my 6th time teaching this class, and actually I was a student in this class 3 years ago. Yeah, and then the first time I was a TA, it was also in this class. So the summertime is definitely like a very special rendition of the class for me. I was a software engineer intern last summer at Citadel in Chicago. So what they do is they do high frequency trading. So they play the stock market game and they try to pinch pennies and make a lot of money that way. So that was a lot of fun. During the school year, I did some research during my undergrad career. So I was involved in the Chung Lab, which we did some eye stuff, some optometry stuff. So basically, we have videos of eyeballs moving around, and I had to extract their positions and their movements and clean the videos and stuff like that and do processing. And then the other lab I was involved with is the Bender Lab at UCSF, and we did some neuroscience work there. So basically, we're just trying to make some mathematical models in code to model the brain. And then last year I discovered bouldering. So I've been bouldering for about a year now. That's just basically rock climbing where you're not strapped into anything, but it's like not that high. I'm not that good at it, but it's a lot of fun. And I also like aesthetic things, so yeah.
Okay, cool. So those are the instructors. Let us know if you have any questions. We're always happy to help. We've been TAs before too, so we really, really enjoy just helping you out in labs or in anything. So just come by our office hours. It doesn't have to be 61B related. Just let us know if you have a question and we'll be there to answer it for you. Okay, so here are a whole bunch of pictures of other people, and these are our TAs, tutors, and senior academic interns. So if anybody's here who are one of those, can you stand up? Yay! Okay, say hi to them, everybody.
Hello, everybody.
All right, so these are the people who are really going to make this course just 100% better. They're here. You'll probably see them and get to know them very well. So thank you guys for all the things that you do for us. Okay, lastly, we have these things called academic interns. You'll see a whole bunch of names here, but these are the people who are not the ones that you see in these photos that are helping you out. So these are academic interns. Their job is to also, they're volunteers, and they're also supposed to help you out with labs or any questions that you have. So make sure to say hi to them when you see them around as well. All right, and the last human of 61BL is you guys. So I wanted to ask you a few questions really quickly just to get to know everyone a little bit better. So it's just, if you fall under this category, just raise your hand so we can just see what the distribution is like in the room. So if you're a freshman, raise your hand. Do you have any freshmen in this class? Few, nice. All right, sophomores, like rising sophomores. A few, all right. How about rising juniors? All right, a little bit more. And rising seniors? Cool, okay, what about grad students? Any grad students in the room? Nice, one in the back. Anyone, a few sprinkled throughout the room, nice. Okay, how about anybody else who didn't fall under that category? Anybody else not one of those? A few? Cool, so we have a very wide distribution of just years in this class, so maybe experiences in college or anything like that. How about people who have, who wants to be a CS major, intending to be CS? Who are those kinds of people? Can we raise your hands? Huh, okay, what about those who are something else, something not CS? Yeah, and there's a lot of you guys. So this distribution is really different from what it's like normally in the semester, which is really cool to see. There's a lot of people who are just interested in this field, maybe want it for something else in the world, and that's really awesome. Okay, last thing I'm going to ask is, who here is a Berkeley student? Raise your hand. All right, visitors from outside of Berkeley, so maybe a different college. All right, visitors from outside the country, so maybe like a foreign country. Nice. Okay, so you can see that there's like it's a whole melting pot. Maybe like during the regular semester you have a similar melting pot, but here it's going to be really different. So I'm excited for what this summer has in store. Okay, so really quickly I'm just going to go over the learning philosophy and the course policies for this class, and then we'll move on to like some more interesting stuff like the stuff you've learned in labs. So really quickly I just want to talk about learning philosophy, so the manner in which learning occurs. So just watch this video. This is a person playing Dance Dance Revolution, which is a game that you like press the arrows on the floor in the order that they come up. So this is a person who has never seen this game before and is trying to play it. Okay, we get the general idea, right? He's kind of like new to this. So let's see someone who has probably gotten a few more hours of experience. This person's playing the mode where you play on both of the boards, so we'll see how that goes. All right, he's killing it here. Okay, so you can continue to watch this video on your own time if you want. He's pretty good, but you can see there's a really, really large difference in the skill level here. This person just saw this. This person's maybe been practicing for a while, and the thing that we want to point out here is that everybody, maybe some of you are here, maybe some of you are here, just know that this person didn't get here just by existing. He didn't just start off being in this position with all these skills. Right? He probably practiced a lot. You have to learn, probably stay in the arcade for like hours and hours on end trying to learn this game here. He probably didn't like try to read up on what the strategy is for the game, or he probably didn't like watch videos of people playing the game. He had to do the game himself. He had to play around, he had to do all the steps, he had to maybe mess up a few times, but he had to put in the work himself and try to get through this game. And he probably went and asked some friends, had them help him with maybe here are some strategies that you can do, or like you ask your friend, like, am I doing this wrong? Those are all things that this person on the right has probably done. So just note that everybody starts here at some point. Right? Everybody are these two guys who have just seen this game and are maybe messing up a little bit, but know that through this experience, like just through practicing, going through the class, you'll be able to eventually be able to get to this point over here. So that brings us into kind of the philosophy for this class. We've flipped the classroom and focused more on these two philosophies, which is active learning and pair programming and collaboration. So active learning, this is why we have you in lab for 12 hours a week. It's supposed to help you get more familiar with the material hands-on. You're not going to learn as well just by sitting in a lecture and listening to three of us talk for hours and hours on end. A more, I think, effective way of learning is actually flipping the classroom, where you are mostly in charge of how the learning is going to happen. All right, so active learning. The last thing is pair programming and collaboration. So partners are mandatory in this course. It'll give you someone to bounce ideas off of, and it's the idea that you can't just do everything alone. Eventually in the real world, you'll have to work with a team that you maybe like or maybe you don't like, but it's going to be more fun that way. You'll be able to tackle much larger projects than you would be on your own. All right, so course policies, I'll try to breeze through this because you've probably seen most of this already, but I just wanted to let you know that these are the main places that you'll get information in this class. So course website, hopefully you guys have seen this already. There's going to be the specs listed, course policies, you can find the staff pictures there if you want to stalk anybody, resources, etc. Those are all going to be there. The next one is Beacon, so beacon.datastructure.es. You might be wondering, why do we have this? This is actually a place to keep track of a lot of the information that might otherwise be floating around, such as who your partners are, how many slip days you've used, what your grades are, who your mentor GSI is, etc. So make sure to always check this for that kind of information. Okay, Piazza. This is our discussion forum for this semester, so just if you have any questions, if you can't reach anybody in person, this is where you'll be posting them, and the staff will be able to answer those questions for you. Gradescope is a place that you'll submit your assignments once you've completed them. They're actually the places that will be uploading your exams, quizzes, and worksheets, and we'll be grading them, and we'll be showing you the grades for that on Gradescope. And the last thing is GitHub. So this is where your code and our skeleton files are stored, so if your computer ever explodes, you'll be able to get your code back using GitHub. Okay? All right, course logistics. So here's just all the things that are kind of happening in the course. We'll have lab 3 hours per day, 12 hours per week, one quiz every week at the end of the week on Fridays. Lecture is going to be 2 hours per week. Exams, we'll have 2 midterms and 1 final, and we'll have 4 projects throughout the semester. So we'll talk about these a little bit more, like in a little bit. But does anyone have any questions right now about anything that we've talked about yet? No? All right, perfect. So now we'll go into a little bit more about the partnership logistics for this class. So you probably have been trying out a bunch of different partners in lab, but the idea is that you'll eventually find somebody that you will want to work with for the remainder of the semester or for maybe at least an extended period of time. So just note that you and your partner must be in the same lab. If not, you will have to switch so that both of you are eventually in the same lab together. The first week, we're trying out a different partner every day, so you at least make a few friends, get to know a few other people in the course. After that, you will be committing to a partner for the duration of a project. So for project 1, you'll commit to one partner, work with them throughout the entirety of that for projects and labs. All right? So after maybe project 1 is finished, then you'll have the opportunity to switch partners. So if you didn't really like the partner you were working with, maybe your schedules didn't work out, this is the time where you can find another partner and try working on projects and labs with that partner instead. So it'll be this kind of commit and then a few buffer days, commit and a few buffer days and commit for the partnerships that are here. So no changing partnerships during the project because you do have the opportunity to break up with them at the end. But just note that both partners must submit their code separately onto Gradescope. So even if you have the same exact code, both of you are responsible for submitting on your own. You might be submitting the same thing, and that's totally okay because you guys are partners, but each of you have to submit your code separately onto Gradescope to get credit. Okay, all right, so labs is the largest part of this course. You'll be here 12 hours per week for 8 weeks. Just note that they're comprised of lab exercises and a worksheet. The worksheet must be turned in at the end of section that day, and that'll be how your attendance is tracked. So you must attend the lab of your mentor GSI, or you will not receive credit for the worksheet for that day. So you might be wondering, what is the mentor GSI? So let me show you by clicking this. This will open up your portal right here. So I'm currently signed in as Jackson here, and Jackson is my student. I'm his mentor GSI. So you have to go to the lab of your mentor GSI, otherwise you won't receive credit for the worksheet for that day. So just make sure you double check this and make sure it matches the one that you want to go to. If that's not the case, you'll have to ask your TA and see if you can perform a swap for that. All right, so make sure you go to the section of your mentor GSI. And if you can't make this lab at all, you'll have to perform a swap. If you occasionally can't make it, email 61bl@berkeley.edu and we'll make sure we have that on record. All right? Labs are due 22 hours after the start of your lab, so this might be a really strange deadline, but the idea is that you'll have the previous day's lab done before the start of the next day. We want to make sure that you're kind of fresh every single day, so you don't have to worry about, oh, well, let me try to finish this previous lab, but also try to work on the current lab at the same time. We want to make sure that the cutoff is really clear. So labs are going to be due 22 hours after the start. No late submissions except when using slip days, and we'll talk about this more later. And note that there is a lab cap, so you only need 57 out of the total 66 points to get full credit on the lab portion. So if you ever need to drop something, if ever something comes up, note that you have a lab cap as well. All right, so we talked a little bit about quizzes, but these quizzes will be administered at the beginning of lab and must be completed in person in lab during that day. So quizzes, remember, they are going to be on Fridays. If you can't make your section, email your GSI at least 48 hours before the lab to let them know and try to coordinate something. But note that if anything does happen, you can't make it, there's also the quiz cap. You only need 15 out of 24 points to get full credit on the quiz portion. All right, so projects. There are 4 projects, and project 0 is solo, but all the other ones are going to be partner-based. So we just talked about Enigma. It's a lighter project, which is supposed to be like a finger exercise to get you familiar with Java syntax. We'll then be going on to Dex, which is going to be your opportunity to create your own data structure from scratch. Next on is going to be Gitlit. So you'll have a heavy design-oriented project, but you'll be implementing your own version of Git. So you probably hate it now, but you'll learn to love it later. The last one is going to be Bear Maps, which is giving you practice extending an existing code base, which is kind of what you're going to be doing in the real world. You're going to be implementing a route finding application similar to Google Maps, and you'll be able to do that all within the span of this class. So I think that's pretty cool. All right, so exams. I'm sure you guys are excited about this one. These exams are going to be closed note, except you can bring some cheat sheets, so we'll let you know what that number is when the time rolls around. These will be pretty hard, so just expect 60-ish% medians. Don't worry, it'll be okay. Don't worry about it. We have this exam supersession policy, so if you show improvement on the final, you can boost one of your midterm scores. So if you don't really do too hot, maybe on midterm 1, and you kind of do the work throughout the semester and get better, and on the final you like kill it over there, then we'll be able to do some sort of replacement. And you can see that formula that's on the course policies. Exam dates are here. Make sure that these work for you, and if not, if you cannot make any of these times, email us immediately. So by the end of the first week, have an email sent out to us, because we will not be hosting any alternate exams. But if you have exceptions, like you have a direct conflict with another final from another class, then we'll try to work something out with you. But otherwise, no alternate exams. If you end up missing a midterm, the exam supersession policy will kind of take over and we'll fill that in for you. Yeah, keep these dates in mind and just make sure that these work out for you. If not, send us an email as soon as possible. Okay, course grade. So here's the breakdown. This is all listed on the course website as well, so I'm not going to talk too much, but just note that there are midterms, finals, projects, labs, and quizzes. Grades are not curved, so they're not based on your relative performance to your friend, so there's no incentive for you to kind of like screw your friend over by like telling them the wrong thing or like giving them the wrong deadline. It's all going to be you, so just focus on yourself, make sure that you're doing the work that you want to be doing, and if you have any other questions, just see the full details about grading listed over here. All right, so I'm just going to quickly talk about the lateness policy. We know that this course is really fast-paced, and we really, really want to make sure that you stay caught up with all the material. Right? Like there's a lab on Monday, Tuesday, Thursday, Friday, and if you don't finish Monday's lab and you try to do it on Tuesday, then you have 2 labs to worry about at the same time. And if you don't do Tuesday's lab, then you wait until Thursday, then you might have 3 different labs to worry about at a single time. So we really, really want to make sure that you stay caught up, because it's going to be hard to kind of catch up once this snowballing has happened. So we want to make sure that like we craft our policies around this idea. We know that like even though this course is fast-paced, like things might happen sometimes. Like maybe you didn't get enough sleep yesterday and you can't think right, and in lab you're having trouble debugging something, or maybe like your friend has like maybe an emotional breakdown or something, and you got to help them out. Like there are things that happen, and we totally understand and see how that can happen during the course of a semester. So we've crafted these policies around this idea to give you extra time sometimes when you do need it, but still encouraging you to stay on top of the material as well as possible. So something I actually didn't mention explicitly was that labs, you cannot turn them in late. That's the idea that we want you to stay on top, but here are some of the late policies that might help you in the case that you can't get that done. All right, so, it's right here. So labs turned in late will not receive any credit, so make sure that you keep that in mind as you're trying to plan out your days and how much time you want to spend on the labs. But there are going to be this thing called slip days. So there are 4 slip days total, 1 released every 2 weeks, and they will accumulate if you don't use them. So if you, let's say you have a slip day this first 2 weeks, you don't use them, then the start of the 3rd week you'll have 2 different slip days, and then the start of this 5th week you'll have 3, start of the 7th week you'll have 4. All right, so using a slip day will extend your deadline by 24 hours. You cannot use a fraction of a slip day, and you can only use at most 1 slip day per assignment. So that's to ensure that you don't get too far behind on the material. And if you need to use a slip day, just send an email to your mentor, GSI, or the TA that you normally see, and then they will input that into Beacon for you. All right, so the late policy for the projects is slightly different, and the idea is that we want you to, it's the same idea where we want you to make sure that the project 1 is done before project 2 begins, project 2 is done before project 3 begins. So any projects turned in late will result in this following penalty. So if it's within 24 hours of the deadline, then you'll have a 10% penalty. 48 hours, it'll be 50, and more than 48 hours is no credit. So just keep this in mind as you're planning out your hours. You do get credit for projects if you turn them in late, but for labs you will not, unless you use slip days. Okay, so any questions about these policies that I've talked about? Yeah?
Do you have to, so if you're going to use a slip day for the lab, do you have to email your GSI before the original deadline, or can you do it after?
Okay, so the question was if you want to use a slip day, when do you have to email your TA? And it should be before the deadline, because otherwise they can't grant retroactive extensions, so just make sure you send that in sometime before the deadline. All right, any other questions? Yeah.
Are the office hours just for logistics, or can you also have like content-related questions?
Okay, so the question is, are the office hours, I'm assuming instructor office hours?
Yeah.
For logistics, or can you ask any type of question? And it's any type of question. You can ask debugging questions, logistic questions, what to do after this course is over, like where to eat. You can ask us anything. All right, any other questions? Okay, well, if something comes up, just post on the live lecture thread because we'll be there, we'll be monitoring it, so we'll give you a really timely response. But one thing before I go is I just want to talk about the academic honesty policies. Just in this class, make sure just to do your own work. We really want to make sure that you're learning as much as you can from this course. So if you ever feel like stressed or anything, just remember these policies and try not to like violate any of these. You really don't want to have to like catch you for cheating or anything, so just keep these policies in mind by you and your partner alone. Do not possess or share code, and remember to cite your sources. All right, so if you get something from the internet that is like a small thing, you can definitely include that into your project, but if you find like a solution for something, stay away from that. So just don't cheat, please. It kind of ruins like your experience as well because you won't be learning as much as you can, so just please don't cheat and everything will be good, all right? Cool, so now we're gonna go on to like cool content stuff. So I'm gonna switch over to Matt, and Matt will talk more about primitives and references and what you've learned in lab this past week.
All right, hello everyone. So this is the fun stuff. We're gonna actually start diving into the material now. If you haven't found the slides yet, they're on the course website on today's like little box. So if you want to follow along, you can. But yeah, let's go ahead and get into it. So what do you think? So here I have int x as a statement in code, and we learned yesterday that you can illustrate it kind of like this. Just put a box and int x next to it. All right, and then if I say x equals 2, what is the correct way to annotate that in my box and pointer diagram? Is it option A, where I put the 2 just directly inside of the box, or is it option B, where I draw an arrow to another box with the 2 in it? So raise your hand if you think option A is the correct way to do this. Okay, and now raise your other hand if option B is the right way to do this. Oh, okay. So the correct answer is option A, right? And that's because x here is an int, and int is a primitive, right? And because it is a primitive, we want to put it directly inside of the variable box. Right? If x was not a primitive, then we would do something more along the lines of option B. All right. So just to formally recap the rules, this is what it looks like. So in Java, all variables have a type, right? And so Java is a strongly typed language, which means that you always have to explicitly label what type every variable is, right? This is different than Python, where it's kind of like hand-wavy sometimes, and sometimes you're not sure what type of variable is, and you have to print it out to figure it out. So Java, everything is explicitly defined, and that just helps with compilation, right? When you compile your code, it's going to check to make sure you don't do anything funny, like mix 2 types together, and then it's going to run it after it does the sanity check, right? But Python, it's an interpreted language, so it just runs everything all at once, and if something explodes, then it explodes, right? We like things exploding in this class, I guess. Okay, so there are two different types of data types in Java. So there's primitive types, and these are the 8 primitive types in Java, and these are the only 8 ones: byte, short, int, long, float, double, boolean, char. There's a little bit of debate. It stands for character, so maybe it's char. I don't know. But all of these will take on default values, and so this is like kind of like 0-ish values. So like 0 for an int, or 0.0 for a double, or false for a boolean. So just these will take on default values when they are fields in a class, all right? And then similarly, we have reference types. So reference types are basically any other type that you want to define in Java. So you've actually already defined a couple reference types. We defined the hello world class, right? The path class, the account class. So all of those are data types that, because you wrote a class file for those, you can use those as data types, right? And all of those will have a default value of null, because null is kind of like a 0-like value, okay? And then when we draw box and pointer diagrams, yesterday you learned that primitive types are going to be drawn directly inside of the memory box, whereas reference types, you're going to draw an arrow pointing to the object. All right. But why are we doing this? Why are we drawing the pictures like this? So let's go kind of on a lower level a little bit. Let's talk a little bit about how stuff is stored in your computer. So your computer stores everything as zeros and ones, as you've probably seen from the movies, right? And basically it's like, is there electricity here or is there not, right? So 0 or 1. And so if we want to represent something like, say, 72, it's going to be represented as just a bunch of zeros and ones. So here it's 0, 1, 0, 0, 1, 0, 0, 0. All right, so that's 72. Another example, 205.75, that's stored as another long sequence of zeros and ones. The letter H is stored as also 0, 1, 0, 0, 1, 0, 0, 0, 0, right? And so, wait a minute, 72 and H have the same 0 and 1 representation, right? So how does it tell them apart? Well, it's going to have this data type associated with it, right? So if we get that sequence and we're told that it's an int, okay, then that means it's a 72, right? But if we're told that it's an H, then the computer knows to interpret it as an H instead, right? If we're told that it's a character, right? And so depending on what the type the Java variable is, these series of zeros and ones will be interpreted differently, all right? Okay, so when you declare a variable in Java, so that's when you call upon it for the first time and you say like int x, right? That's declaring a variable. Your computer is going to set aside enough bits for you to represent that variable, right? So for an int, it's going to give you a bunch of it's going to give you 32 bits, right? And that's going to be enough to hold your integer. If you want to double instead, since that's like a decimal and it's maybe a little longer, it's going to give you 64 bits instead, all right? And these box of bits will not be filled until you initialize the variable and tell it what number you want to put in it. All right, so here's a little example. So in the first two lines, I'm doing my declaration, int x and double y. Those are declaring those variables. And when I do that, I'm going to get empty boxes to hold my numbers, right? So I have a size 32 box for my int, size 64 box for my double. And then when I get to lines 3 and 4, when I actually set them to numbers, then it's going to be filled with the 0 and 1 representation of those numbers. So that's what x looks like, and that's what y looks like. It would be a little evil for you to have to write out this 0 and 1 representation on an exam. So we'll save that for 61C, and instead, let's just put human readable numbers in these boxes instead. All right. Okay. So that's kind of why we're annotating primitives in that way, because we're literally getting a box of bits, and then we're just representing them in zeros and ones, and we're just kind of writing them in numerical form instead so that it's easier for us to read. On the other hand, we have reference types, which are non-primitives, right? And by the way, we can tell the difference between what a primitive type is and a reference type is. We don't have to memorize the 8 ones because it's the way they're named, right? So by convention, primitive types are all lowercase names, like int is all lowercase and long is all lowercase. But non-primitives typically start with a capital letter, and it's good style for it to start with a capital letter. So for example, here, potato starts with a capital P, right? Okay, well, so anyways, what's going on with reference types? So when we create an object, so when we instantiate it, so that's when we say new potato, and we call upon the constructor, so like 101.2 with the arguments, right? It kind of does a similar thing, right? So Java is going to allocate enough bits for you to represent your object. So in this case, a potato has both an int weight and a double height. So we're going to need enough space to hold both an int and a double in order to represent our potato, right? And so what it's going to do is it's going to give you enough bits to do that. So here, the green numbers are the int, and the blue ones are the double, right? So we have 32 plus 64 bits here, and that's enough to represent our potato. And then what happens is the constructor that you write, the code that you write in your constructor typically sets values to these bits, right? And so what happens is that it fills them with 101.2 in the binary representation. And what it returns is it returns the start of all of these bits, right? So because the green numbers and the blue numbers are next to each other, like it knows to tell you that like the potato starts at the beginning of the green numbers, right? And so all we have to do is Java is going to return that address. So it's that number of bit. It's the 238. I missed a comma. 23847234423 bit in your computer, right? So that's just like an address on a street, like maybe, I don't know, like 100 Durant Way, or is it Way? I don't know. It's Durant something, Durant Avenue. So it's just an address in memory. It's where your potato is living in memory, okay? So that is returned by a call to the constructor. Okay, so this is where the potato is living, but how do we find it again? I think I go to the next slide. Okay, cool. So yes, so we're going to get a box of bits, and it's always going to be allocated as 64 bits because that's how many bits we need to remember an address. Okay. So this is what it looks like. And so in this example here, potato P, and then setting P equals to null, so the address for null is going to be represented as zeros. Null is not actually like a place in memory, but it's just like the presence of nothing, the nothingness, right? So it's just going to be all zeros. It's not actually a place. But if we were to store the address of the potato, then what we would do is potato P, and we can say that that P equals a new potato, right? And so that new potato is living in memory, and then we're going to store in our potato P variable the number that represents the address as to where the potato is living, all right? And so our potato P is this number, which again is the address and where it's living. It's this red number here, right? Okay. And again, we don't want to write out these long series of numbers, so we can just represent them not using a number, but representing what it means, right? So this means an address, so that is where the potato lives, and so we'll just draw an arrow instead to our instance of the potato, right? Because that box is representing where the potato lives, so this arrow is pointing to where the potato lives on a piece of paper. Yes, question?
Is null a primitive or reference?
Null is like a value. It's like 0 or something. So it's like, it just represents 0, but for objects, yeah. Yeah?
Address takes up 64 bits, but the weight and the height for the potato eats up more bits than that. How is that possible?
Yeah, so just a slight simplification there. You're right. We will need a little bit more information to remember like what constitutes a potato, but it's going to be something like that. Yeah. Awesome. All right. So why was Java designed this way, right? So this is kind of weird. Like, how come some like things are represented like directly in the memory box, and how come sometimes we have a address to an object? Like, why don't we just always store like the whole thing, or why don't we always just store addresses, right? So imagine this: after you take 61 BL in the summer of 2019, you get really good at programming, and you want to get a job, right? So maybe you land an interview at Google, right? And so you're interviewing at Google, you ace all the interviews because you've learned so much in this class and you've done so well, and the recruiter wants to hire you, right? But before they hire you, they always do one thing. They always want to make sure you haven't lied on your application, right? So they typically want to ask you to put them in contact with someone you know in order to like kind of validate everything you've done. Like, oh yeah, I know this person, and you know they have done all this stuff, right? And so there's a couple ways that you can do this. First of all, if you have your friend, this is your friend here. If you have your friend, one thing that you can do is you can create a clone of your friend and drop them off at the Google office and give them to the recruiter. Unfortunately, I don't think your friend would be too happy if you cloned them, so that's not typically what we do, right? Instead, what we do is we give your friend's phone number to the recruiter, right? Because it's too cumbersome for us to clone our friend, right? And so it's kind of the same way in Java, right? Like we have all these complicated objects that are reference types, but like it could be very expensive for us to clone those objects. So instead, we're just going to pass along a phone number so that we know where to find our friend, okay? Now, why don't we just pass along addresses to our primitives as well? Well, an address is 64 bits, an int is like 32, and a double is also 64. So why would you have a 64-bit thing that's pointing to another 64-bit thing? Just store the 64-bit thing, right? So for primitives, it's like kind of dumb to have a phone number to another number, so we just store the number directly, okay? Okay, this brings us to the golden rule of equals. Basically, the golden rule of equals goes like this. So if we have a statement that looks like B equals A, so this is just a common assignment statement that you've probably used in the last 2 days, right? Basically, what this means is evaluate everything on the right-hand side of the equal sign. So evaluate A and take that result and put it into B, right? And so when we say that, we actually mean that we're going to copy the bits from A into B. So pictorially, this is what it looks like. Okay, so we have these 3 lines, and then on the last line, we say that y equals x. So when we say y equals x, what we're going to do is we're going to copy the bits from x into y, right? And x is a primitive int, so we're going to be copying the actual primitive that's inside of x into the box that is y. So we're going to copy it, and in our box and pointer diagrams, we don't want to put zeros and ones because that's too hard, so we can actually just put the number. Right? So when we copy primitives using the assignment statement like that, we're going to copy the primitive directly. And notice now there's 2 primitives that are living. So if x changes, y is not going to change because they're not linked, they're copied. Right? But on the other hand, if we're going to be working with reference types instead, so now I've changed it back to the potato, if I say q equals p, then what actually happens is that we're going to copy what was in p into q, right? And so p is an arrow, right? And remember, the arrow pictorially represents an address, right? Which is just a phone number to where our potato is living in memory. So when we say that q equals p, we're going to copy whatever is in p's memory box, which is that address, and we're going to copy that address into q. And so that's why, basically, q is now going to have an arrow pointing to the same potato, right? Because we've copied the address from p into q. Notice that we have not cloned our potato, we've copied the phone number to it. Okay? And so the implication of this is now, if we go into p and we change something about p's potato, since it's the same potato, like q's version of the potato is also going to change. Right? So that's kind of like a subtle difference between primitives and reference types. Okay, any questions before we move on to the next part? Okay, so now let's kind of recap some of like the trickier points in yesterday's lab. So one of them is the keyword this, all right? So the keyword this is kind of like self in Python. It's the current instance of the object you're working with, right? And so when you call a non-static function, you're going to have access to this instance, right? And the reason for that is because when you have a non-static function, you have to have an instance of the object in order to call it, right? And so we can annotate it in our box and pointer diagram. So let's take a look at our visualizer. Actually, I think I have it set up in another tab, if I can find it. Oh, I get to type it myself. We can do this live. All right. Okay, so I have my dog class here, and I'm going to first put a field for my dog. So maybe I want to have a name for my dog, right? So the fields I can put at the top. Oops. Okay, so that's my field, and now I can put a constructor here, right? So these are the parts of the class we learned yesterday. Fields, constructors. Okay, so this is my constructor, and typically what a constructor does is it takes the arguments that it gets and stores those values into the fields, right? So in this case, I want to store my string name into the string name that's the field. So because they're both called name, there's ambiguity into which one is being referred to. Like if I just say name, you don't know which one I'm talking about, right? So basically, in Java, it's decided that if I just say name, it's referring to this one here. And if I say this.name, it's referring to this one here. So in order to do this assignment statement, I can say this.name equals name. Okay, and now I can put a method, right? So a method is just something that this class can do. So something that my dog can do is maybe it can tell me its name if it can talk. Okay, cool. So I have a field, I have a constructor, and I have a method. And remember, in order to execute my program, I have to have a main method, which is why I have it here. The main method could live in a different class, but if I want to run this class, it has to have the main method here, right? So let's do a couple things. So first of all, let's make a dog instance, and then let's call the print name method. Okay, so I've made an instance of my dog called Christopher, and I'm going to call the print name function. So let's see what happens. it says, error, non-static method print name cannot be referenced from a static context. And this is because, right, we said that print name is a method, and actually it's a non-static method because there's not the word static in this method header, right? So print name is a non-static method, and we just said in that slide that in order to call a non-static method, you have to have an instance of the class in order to call it, right? So here, I'm just calling print name. There's no instance of the class, so it's not going to work. So what I have to do instead is I have to say, I have to use this instance of my dog called CRISPR, and then I'm going to have to use dot notation to call the print name function. Okay, so now it works. So let's kind of see the diagrams as to what's going on. So I'm going to create my dog, and it looks like that. What a pretty dog. Okay, and then when it calls the print name function, it's going to go over here, right? And notice in your box and pointer diagram that there is this labeled here. So you should also put this in your box and pointer diagrams when you're calling a non-static method, and that's because I'm allowed to access this inside of this method, right? So here I'm doing a print line, and I want to access name, the name field that belongs to this instance. So I can go over here to my dog and fish out the name, which is CRISPR, and I can print it. All right? Yes?
Make it bigger.
Oh, can I make this bigger?
Like
this bigger? Oh. Okay. Does everyone see that? So you want to put this inside of your function call because you have access to this in a non-static method. Oop, oop. Where did the slides go? Here. Okay. Awesome. So that is the keyword this. So now let's talk about static methods, right? Because we just did non-static methods. So if I have a static method, well, I don't require an instance of the class in order to call it, and so I can't rely on access to this because static methods don't need an instance to be called, right? So let's take a look at what that looks like. Edit code. Okay. So let's add a static method into here. So maybe I'm going to add a static method called bark because all dogs go woof woof.
Can you zoom in?
Yeah.
Using, oh,
Is that good? Okay.
yeah.
Okay, so what did I do here? First, I added a static method called bark, and then I tried to call bark using an instance of my dog, and it turns out it compiles and runs. So this actually works. So I can click, and I know you can't see all of it, but it finished without an error, right? So this works. But it turns out you don't need an instance of the object in order to call the bark method because bark is static. So if I edit my code and I just change this to like a dog, like this, which is the name of the class, this will actually work because bark is static. Okay, so I skipped ahead to where we're analyzing bark now, and if we look over in the diagram, well, I feel like I'm swimming in like water right now. Okay, so if we go over here to the bark frame, you notice that there is no this here, and that's because we didn't have an instance when we called the static method, and you can't rely on that, right? And so actually, what would happen if we did something like this? It's hard to speak without using the word this. Okay, so what if I wanted to put something like this here? So what if I wanted my static method to print out this.name? Now remember, we don't have access to this, so what's going to happen? Let's see. Aha, we get an error, right? So Java doesn't let us do this because it knows, and we know too, right, that static methods don't have access to this. So what does it say? It says, I know it's hard to read, I don't think I can zoom this in, but I'll read it slowly. It says, non-static variable this cannot be referenced from a static context, all right? And so what does that mean? Well, we are in a static context here because we're inside a static function, and we're trying to access a non-static field, right? And that's a problem because a static function does not require an instance to be called, but we're trying to access a field that belongs to particular instances. So that's not allowed. Okay. Great. So
What if we don't include dog in dog mark?
if we don't include dog here, let's see what happens. Let me delete this line that causes it to fail. And it turns out it compiled, right? So actually in this case it's okay because this main method is inside of the dog class, and so it knows that we're referring to this bark, and it doesn't need an instance to be called, so it's perfectly okay with that. Good question. Okay. So now let's talk about static fields. So we can have static methods. We can also slap the word static on a field. So what happens when we have a static field? A static field is shared by all instances of a class, so sometimes it's called a class variable, right? And so no matter how many dogs you create, they will all share the same static instance, okay? Okay, so let's take a look at that. So maybe for my bark, instead of having the string here, maybe I want to turn this string into a static field. So let me put this up here. Okay, so what did I do? I just added a static field called noise, and remember that static fields are shared among all instances of my dogs, right? And so actually what happens is before we start running anything else, the first thing that we do is we allocate our static field, and then we're going to initialize it to this woof woof here. So that's the first step, and I'll have to go down here to click. So let me click a few times first. Okay. So what happens? So we have like this static field section of our box imported diagram that before we analyze any of the code in the main method, like right off the bat, what we did was we said, okay, the dog class has a static field called noise, and all dogs are going to share this noise field, right? And we also said right away that it's going to be initialized to woof woof. Okay. So before we do anything, we set aside that space in our box imported diagram. Now we can go down here to our main method and do everything we did before. So click, click, click. And then we go over to bark. So now we're analyzing bark, and we're trying to access this static field, right? And so what it does is it wants to print out noise. And luckily, noise is a static field, and we're inside a static context, so that's all fine. We can access this, and it prints successfully. So if I skip to the end, you can see here that it says woof, woof. All right. Is anybody getting car sick or anything like that? From me kind of scrolling around? Okay. Sorry about that, but hopefully you can see what's going on. Okay. So before we did that thing where we said, okay, we're inside of a static context and we want to access a non-static field. Is that okay? And we said that no, right? We're going to get an error because you can't do that. What if we do the opposite? What if we want to access a static field inside of a non-static context, right? So what if here inside my non-static context, this non-static method, I want to access my static field. Can I do that? Let's see. So let's say, let's say this.noise even. Will that work? So I'm starting it up, and let me skip to the last thing. And yes, it worked. So that's fine. Oh, wait, wait. It worked. Okay, so it's still calling bark. It's not calling print name, right? So actually that was false hope. So let's change it. Whisper.print. Oh, nope. Okay. Aha, okay, so now it worked, right? So first it printed out its name, and then it printed out its noise. So that means that we are allowed to access, so when we're inside a non-static context, we can access static fields, right? But as we saw 5 minutes ago, we can't access non-static instances inside a static context, all right? So if that was confusing, which it is, you can go back to the slides and click on the links and run this demo again, okay? Okay, the very last thing I want to show you is equals equals, all right? So equals equals is a way for you to check whether two things are equal or not, right? But we'll learn later that there is also a dot equals, right? So this is kind of like the difference between equals equals and is in Python, right? There's two different types of equality. So today we're going to talk about equals equals. So equals equals is used to check whether two boxes of bits are the same or not, all right? So what does that mean? So for primitives, that means are those two numbers the same, right? Because those box of bits that we're storing in our memory boxes are the actual values of the primitives, right? So equals equals for primitives will check whether they are the same number. But for reference types, what is those box of bits? Those box of bits are phone numbers to where our objects are actually living. So for reference types, it's actually checking whether they have the same phone number or not, right? So it doesn't matter if our dogs have the same name. If they are two separate dogs, it's going to say, nope, they're not the same. And so if you want to say, okay, maybe if two dogs have the same name and the same fur color, maybe they are the same, then you have to define an equals method and explicitly define what your conditions for saying that they're the same are. Right? And so we'll save that for another day, but let's take a look at equals equals. Okay, one last time. Okay, so let me add some more instances here. All right, let me clean this up first. So let's change this back to just printing the name. And yeah, let me make a few more dogs so we can kind of compare them. Okay, so I still have my dog called CRISPR, and I have a new dog called Mocha. And so I'm going to check whether CRISPR is equals equals to Mocha. And then I'm also made an int x and an int y that are both 5, and I'm going to check whether those are equals equals to each other. Okay, so let's see what happens. So it's doing its static stuff up top right now, right? And then forward. Okay, so now we are making CRISPR, and now we're making Mocha. Okay, so now we are on the print line. So let's see what our diagram looks like right now. So, okay, so we have CRISPR, and CRISPR is pointing to a dog instance, and this is our dog CRISPR. And we have another dog called Mocha, and because we used the new keyword, we have created another instance of a dog, and its name is Mocha. So there are two separate dog instances. So now I'm doing system.out.println, does CRISPR equal Mocha, right? So what it's going to do is it's going to compare whether these box of bits are the same. Is CRISPR's box of bits the same as Mocha's box of bits? No, they're not, because they are phone numbers to two different dogs, so trivially that is going to be false, right? And it prints false down here. Okay, so that was kind of a dumb example. Let me make two dogs with the same name, for example, and see if they're let me make two variables that have the same phone number, and let's see if they're going to be equal. Okay, so let's see what happens here. Okay, let's kind of skip ahead. Where did it go? Okay, so we now added this line where I declared a new dog called Cass, but it's going to be pointing at the same thing as CRISPR, right? And so by the golden rule of equals, what did that line do? Well, it made Cass, and it's going to copy the bits from CRISPR into Cass. And the bits inside CRISPR is a phone number to this dog who is actually called CRISPR. So CAS is also going to have a phone number to the same dog called CRISPR. So now, when we ask system.out.println, is CRISPR equal to CAS? Well, the answer is yes, right? Because they have the same phone number, so it's the same box of bits, so they are indeed going to be the same. So that's going to be true. Okay. All right, very last one, let's look at the primitives. So I declared x and y to be 5. Are they going to be equal to each other? Oh, I went back, but you can guess that the correct answer is yes, they're going to be the same, right? And that's because x and y both have 5 inside of their box of bits. So when you ask, is x equals to y? Yes, they both have 5 inside of their box of bits, and so they are the same. And so that's why we're going to print true as the last output. All right. Any questions as to what we covered here today? Cool, awesome. All right, so now we're going to move into our next section. So Jackson is going to talk about some Git stuff, and that'll be it for today.
Hello. So as I get started with this where to go? I'm closing this. As we get started with this next section, just as a show of hands, who is having fun with Git? We've got actually half the people who raise their hands were TAs, so yeah. Who's not having fun with Git? Okay, that makes sense. Yeah, so basically Git is going to be your best friend and worst enemy throughout this course. I know for myself, I didn't actually learn how to use Git until 2 semesters after I took the course, which was problematic because I had to use Git during the course. So it made for a really complicated time where there's a lot of frustration and not understanding why the heck my things wouldn't submit and where all the merge conflicts came from and why everything is sad. So we're going to try to avoid that. So what we're going to do is we're going to kind of talk through Git and try to explain it and explain how it works, because one, it's good to have an understanding so you know where your files are going as you're using Git, so you're not just yes, they've gone into the sky and they are free and maybe I will find them again and maybe not. That's not really what we're aiming for. So that's one thing, so you know what's going on and you know exactly how to use the commands and everything gets submitted nicely. And another thing is that you're going to have to make Git yourself. So let's try to get a good understanding now, so it's not gitlet the project, it's due, it's the big one, and then you're well, I don't really know how Git works on my own computer, so I don't know how I'm going to make it. So yeah, let's talk about Git a bit. So why do we use Git? So basically, at its core, Git is a version control system, otherwise called a VCS, which is used to manage project files. I don't know what that means, right? Well, basically what it means is it's something that can save different checkpoints of your files as you work on stuff. So that's the easy way to think about it. And then what it does, it allows you to make these checkpoints so that you can always look back and track your progress and say, wow, this is when I made this change at 4:37 a.m. when I should have been sleeping, and then I submitted this at X time or whatever. And it also allows you to restore old versions. So you look and you say, oh, 4:37 a.m., that's when I'm not thinking clearly. Maybe I should undo those things I did. So that's part of why we use Git. Because this allows you to, on your own computer, just manage the files and your own code more efficiently on your own computer. So let's talk about how Git works within a single repository. So we all remember the Git checkoff. That was a blast. I know, it was super fun. But so let's talk about how this kind of works. So just as I know you've seen this before, but who knows if it actually made sense, because the first day is always hectic trying to get everything set up. So let's pretend this box is your computer. And yeah, it's got room for stuff. Let's put some stuff in it, some files. So here's file 1. The first file, it's aptly named. Your computer should use 0 indexing, but I didn't. Here's file 2, and that's file 3. They're nicely sitting on your computer. So the next thing I want to do is I want to say, let's make a project. So I'm going to make a directory somewhere on my computer, and it's got space in it. Enough space for my files. So then what I'll do is I'll say git init in my project directory, and that'll create a couple things. So it creates this git this git directory down at the bottom, which is actually something on your computer. That .git thing, you can look for it. if you say like ls-a, you can find it. This staging area isn't exactly like some file you can look at, but we're going to put a box there because it's going to be useful like mentally as an analogy. So yeah, git init basically comes up with these two things for you. Then let's say I want to put some things into my project directory. So I'm going to move file 1 in, I'm going to move file 2 in. Everyone following so far? 2 files in the project. Cool, life's good. Then basically what I have now is, since this project directory is a Git repository and like Git has been initialized inside, Git knows a few things. So Git knows that file 1 and file 2 are in this project directory. It doesn't know anything about the insides of these files. It just knows, hey, I see some things here that weren't there before. And then if you like ask for a Git status, Git will say like, do you want me to look at them? But what Git doesn't know about is file 3 because it's not inside the right directory. Following? Cool. Yeah, question?
Yeah, is the project directory just like the file under which, or the folder in which you put these files?
Yeah, this is basically lab01-checkoff,
Yeah.
or your repo number.
And then in terminal, like when you're in that folder that you run like get init, then that's when
Yeah.
like is aware of those files.
Yeah, so you'd run git init from inside the project directory. Cool. Awesome. Keep going. So let's say before we've like started tracking anything, we make a change to one of the files, right? So let's say it's now file 1.1. See, 1.1 changed. So the insides of it are different. Let's say it's still called file 1 or whatever it was called, but basically the insides are different. So if you ask Git anything about what's going on, Git will know that file 1.1 is there, and it will know that file 2 is there, but it won't know anything different from when we just had file 1 and file 2, because it has no idea what the insides of these files look like. It just knows they exist. Still, it has no idea what file 3 is doing over there. I don't know either. But yeah, so does that make sense so far? Until you tell Git to like track anything, it has no idea what the insides look like. It just knows that it's there. Okay, moving on. So let's tell Git that we want it to like know what's going on inside these files because we want to actually use the version control system and like follow along. So what we'll do here is we'll take file 1.1 and file 2 and we'll add them to the staging area with git add. So what git add does, as we saw in lab, it pushes the files into the staging area. It doesn't actually like move them around on the computer. It just tells Git that like, oh, these are being tracked now. So now Git is looking at them and it says, all right, I'm ready. You tell me when, I'm ready. You tell me when, and we commit, and now I know what's inside these files. But, you have to commit first. So let's go ahead and do that. So now that Git's tracking these files, it knows that if you want to commit, it'll pay attention to the contents of these files. So we'll commit our changes with git commit, have a nice message. Always remember your git commit messages, because then you're going to look back later and think, my git commit message that says help, I don't really know what I was doing. And also we can see them, so watch the expletives. We know. But yeah, so basically what this does is over there in the .git repository, there's like little tiny like versions of like things that I've done in each file. It doesn't copy the entire file over, as we'll like learn later in gitlit, but what it does is it basically keeps track of changes you've made to that file. So it kind of has like the first version and then all the deltas up like afterwards, so that like if you want to like go back to any version, it just undoes a bunch of changes. Kind of like when you're typing something in your code and you're like, whoa, you just like Command Z a bunch of times. Basically the same thing, kind of. But yeah, so then what happens is now that these are committed, Git's tracking these, tracking the contents, and it knows what's inside. So if we make any more changes, Git will know. Everyone following so far? Any questions? Yes, another one.
Yeah, if you add the file to the staging area,
Yeah.
and then make another change, and then commit it, would it have recorded that change?
Yeah, so what you've done is when you've added it to the staging area, this is a really good question actually. So when you add it to the staging area, you've basically told Git, hey, when it's time, pay attention to this file. And so Git isn't like looking at the changes you've made right then and there. It just knows which file it needs to commit when the time comes. So you can like add something in the staging area and then like modify it. And then when you commit it, it'll still know like to do that file because you've already told it, like track it. But it's always good to re-add your things just in case you forget. So anytime you make a change and you want to save it, I would say go ahead and say git add all over again. Better safe than sorry. Good? Okay, moving on. All right, so now that Git's keeping track of these files, let's make a change to file 2, right? So now it's like file 2.2. You know, we had 61b.txt, 61bl.txt. We did this kind of thing before. But now if we make that change and we ask Git, then it'll basically know that something in file 2 has changed since the last time we committed it. So it knows the difference between file 2 and file 2.2. So then if we wanted to, we can easily revert the changes by using git checkout, where you basically say git checkout repo number and then the file name. If you just throw the repo number in, you'll get this weird detached head state and you'll be sad. That's actually one of the reasons why I got a bunch of points off on one of my projects when I took the course, because I didn't know how to fix it. So let's try to avoid doing that, and then we'll learn how to fix it, so it'll be okay. But basically, with checkout, we can revert to earlier versions of the file. So we can go to 2.2 if we commit it again, or if we don't commit it. Regardless, we can go back to version 2 because it's saved. However, with version 1.1, since we only started tracking it after it was version 1.1, we have no way of using Git to get back to it. So if you remember in the Git exercise, we had version 1, 2, and then 3, and then we had you go back to versions 1 and 2, and then if you think about it, how do you get back to version 3 if we didn't commit it? It's gone. So if you don't commit anything, you can't get back to it, so we can't get back to 2.2, and then any previous versions we can't get back to. So Git can only pay attention to what you told it to pay attention to. Kind of makes sense. Okay, does that make sense? Any questions on Git with a single computer? Yes, I'm ready.
Yeah,
We can just have you sit up here next time.
the way you're saying about having to add the file name after the come through and use checkout.
Yeah.
Is that like when you like go to get log and then see like the first 4 digits of the number?
Yeah.
But then you also have to like specify which file
Yeah.
you want.
Yeah, so basically, if you have a file and you want to return that file to a certain state it was in before, you have to say, hey Git, I want you to check out, based on a certain commit ID, this file. So you have to tell Git all the things, otherwise Git doesn't know what you're asking for. If you just say check out an ID, it'll think, all right, like here we go, we're going back, all of them, which is, you know, not necessarily what you want to do.
Yeah,
Go ahead.
But if you want to do all of them at once to that version, then you can just do the number, right?
Yeah, it'll put you in a weird state, so let's not do that. What you can do is you'd want to check out like specifically the files you want. Like it will do something similar to what you're thinking about, but not exactly what you're thinking about. So like yes and no, but I really would suggest not doing that. There's another way to revert back to like everything, but like I wouldn't check it out like that. It'll cause the problem that made me lose a lot of points. I would have gotten the next grade bucket, but I didn't. Cool. So, any other questions so far? Okay, so this is kind of like that covered up to what we already did in the lab. Everyone already knew that. I was just talking. You didn't even need to listen to that. That's fine. But here's the part that gets really fun and is where like the true horrors of Git arise. So basically, the important part about Git is not only is it useful on one computer, we can use 2 computers. Or many more than that. So let's say like you have a computer and you have Git on it, and then you have another computer and it has Git on it. You can actually send files back and forth between those 2 computers and like keep track of them using the internet. So instead of using like some people, like you can, if you really want to keep your files secure, you can put them on a USB and run them over to your partner and hand them the USB. Not that effective. Also, something that's not effective that I may or may not have done in the past is using Messenger to send your files. Bad idea, because things get confusing really fast. So we're giving you the tool Git, and we're hoping you'll use it because it's super useful. So if we want to use multiple computers, we can use the fact that Git is a distributed version control system, which means you can like incorporate changes from various sources. Your laptop, the lab computer is your friend's computer, etc. When I say your friend's computer, I mean like your partner or your friend if you're working on a project that's not in our class. Collaboration policies, don't go overboard. Yeah, so basically what we're going to do in this class, we're going to connect Git to a code hosting website, in this case GitHub, and this will help us remotely access our project from any Git-enabled computer. So that way you can write your stuff on your laptop, send it to Git online, forget your laptop, go to lab, panic a sec, remember that we've got GitHub, and then use a lab computer to keep working. Awesome. So yeah, we'll use Git and GitHub, and then we'll use that to submit to Gradescope, as you've probably noticed by now. So yeah, how Git works between repositories. So this is if I have like multiple repositories. So let's say, for example, you have a computer, and then we'll make a project repo inside, and then let's say you have a GitHub repo. So it's like your computer, and then one of those like SU19-S23. I think that's me. Maybe, I don't know. But so we have these two spots where there's basically repositories where we can put files and move things. So what we'll do is we'll take your project repo and we'll make a couple files. So then you can git add file 1, git commit added file 1, solid message, could be better. I don't know what file 1 has, so I didn't make a better message. And then let's go ahead and git push it. So we'll send it to the repo. So now it's over there. Because it's my repo, didn't have anything on it, they were in sync, and now this file's over there. Did it move out of my repo? No, it's still there. We've basically taken our current state of our Git repository and sent it over there and copied it, and now the repository has a full copy of all the work that I've added, committed, and pushed. So remember, if you want to send something to your repository, what are the 3 steps? Are there more than 3 steps? I think there's 3. Add, commit, push. I guess the first step is to make the thing that you want to send, but yeah, so like 3.5 steps. So make sure you have the thing you want, and then add it, commit it with a good message, and then push it. And then that'll send it to where you want to go. So you can't submit stuff if you haven't pushed it. Yeah. So then let's say that there's also this skeleton repository where you use to get like your lab files and stuff. So how does that interact with all this? Basically, the skeleton isn't hooked up to your GitHub repo, but your personal repo has a connection to it. So you have 2 connections. You have a connection from your computer to your repo that's like remote, and then you have a connection from your computer's repo to the skeleton that's also remote. So what you can do is you're allowed to push things to your repo and pull things from your repo, but you can only pull things from our skeleton repo because we don't want you putting random things where everyone can see it. Make sense? Okay, so you can always pull from the skeleton repo. So then what we'll do here is we'll go ahead and say we'll git pull skeleton master, and I'll pull whatever code. So now we've copied over whatever code that there was in the skeleton, and now we have it on our computer. Okay, we're following so far? Yes. Yeah, okay, I got one. Cool. So then let's say instead of doing this class alone, which would be sad, we have a partner. So what we'll do is we'll have your computer and we'll have your partner's computer, and then notice this is now your shared repo, so I just changed that. So this is one that you're both sharing. So don't add your partner to your personal repo, just your shared repo. So then what will happen here is let's say that your shared repo has like that file 1 on it, and you have your partner's computer and they want to like get the stuff that's from the shared repo. So what they'll do is they'll say git pull origin master because they're connected to the same repo, and they'll pull that onto their computer, and now you've got a file 1 and they've got a file 1 and your shared repository has a file 1. Everything's good, right? Well, what happens if you want to start editing things? So let's say you make some changes, file 1.1, you add the file 1, you commit the file 1, and you push the file 1. And you sent it there. So now you have, okay, so first you have file 1.1, and then the shared repo is file 1, and your partner's computer is file 1, right? And then you've both made changes. So let's say you have your version, you push it to the repo. So now you have your version, the repo has your version, and they have their version, right? So now we have multiple versions of the same file. So what we'll do now is we'll have, oh, like your partner said, I made some changes too, I'm gonna push them. So what'll happen here is if they try to push and they reach a point where they're basically like not caught up because you've made changes since the last time they pulled, it's gonna throw like an angry message and say, hey, there's been changes since the last time you tried this, you should pull. Like, you can't do this yet. So what they'll have to do is they'll get rejected from the push, and they'll have to say git pull origin master, and what that'll do is now on their computer, they'll have a file that has their changes and your changes, and then they have to do this thing called resolving a merge conflict, where you basically say, all right, I have to decide, did I do this right, or did my partner do this right? And whoever's resolving the merge conflict gets to decide. So, you know, that's up to you and your partner. But basically what they'll do is they'll go through the file and they'll adjust all the like weird Git stuff that shows up and tells you that there's a conflict. And then once they've resolved it, then they have a version that has both of your changes in it. And then from there, they can go ahead and add, commit, and push it because they now have like all of the history. They know what changes like happen on your computer, and they can go ahead and push it, and that'll override the changes on the shared repo. Now the shared repo has both changes. So now, what do you want to do here? Do you want to make more changes and push it? No. The first thing you're going to want to do before you ever push is you're going to want to pull, because that way you'll be up to date, and then any changes that you make will happen like after your partner's changes, and you're not trying to make parallel changes that can lead to a merge conflict. Okay, questions? Did that make any sense? Nice, I got like a couple nods. So, one question?
So when they like merge the file and then send it to the repo,
Yes.
why doesn't it just block them again? It's still like a different file that's in the repo.
So it basically keeps track of like the order of the history. So when they merge it, so when they've pulled it and they get that merge conflict happens because they can see, oh, your version was the one that was on the repo, and then my version is the one that I have, and then they pull, like, I need to get the pronouns right. Okay, so they have their version, and your version was on the repo, so they pull your version from the shared repo to theirs. Now they have both. So they have all of the changes that have ever been made to that file, right? When they merge it, that has all the changes that have ever been made, and then they make one additional change. So then when they go to push it from there, this merged version, they have their data on their computer, and then they have their repo data, and they're like, basically what Git does is it compares the differences between them, and it can see that their version is more up to date than the shared version, and therefore it can safely overwrite it. Does that kind of make sense? It's like because they have all of the information instead of just part of the information, because the merge conflict is if you just have part of the information.
So it's because they pull, it's like, okay, it's fine, just take whatever.
Yeah, so they have all of the possible knowledge about this file, and now that they have it, they like fix this merge conflict, and then they can send it back up and say like, look, I have all of the information, I've decided what it should look like, go. And then once it's there, then the shared repository knows, however much information is they knew when they pushed it. So then when you pull it again over here, you're gaining all that like history, and now everyone's up to date. Does that make sense? So basically, long story short, pull before you push. Yep.
Does merging require your partner to copy and paste in a text editor everything they think should be in the file?
Kind of. I'll show you in a sec. I'm going to demo this, like this thing. I'm going to make it happen right in front of us, so it'll hopefully make more sense. But yeah, basically when you want to like fix the merge conflict, Git will add a bunch of like stuff to the inside of the file that you have to erase because it's like special Git characters that it uses to keep track of things. So they get like cleared out.
Since if you make a change and push it to the shared repo, and you're working, say, in a different location than your partner, how would you avoid the merge conflict at all, since your partner's file on their computer is going to be different from what's in the shared?
So if you pull before you push, then basically your computer will, before you want to start working on anything, you pull the changes and fix stuff on your computer and then send it in. So basically the merge conflict comes from you working on your computer as I'm working on my computer, and then we both push. Whoever gets there first is like, cool, that worked. Whoever gets there second is like, what just happened? There's a merge conflict, because Git doesn't know who's right. So Git isn't gonna decide you know what, this person pushed first, so therefore all other changes are just gonna get deleted. It values both of our changes equally, and so it has to tell us, hey, one of you needs to decide which changes are the correct ones. Yeah.
How does Git know if the file is an updated file or if it's a completely new file?
How does it know the difference between I'm seeing this for the first time ever and there's been a modification?
Yeah.
So that's after you've added and committed it. That file's now being tracked. So in the Git repository, or in the .git directory, it has information that says these are the files I know about, and then it can keep track of any modifications to the inside of them. So yep.
So it keeps track of them through the address, not the name.
That's more than you need to know for now. But I guess for Gitlet, you can probably keep track of it from the name. But it keeps track of basically if you change the name, it'll like think that you've removed and then replaced the file with something else. Like, it gets pretty smart and it can detect if you've done that sort of thing. So it'll know if you've like changed the name, basically, if that's your question. Yeah, kind of. Cool.
So if you
Go for it.
pull the field from the repo, and you will get the field in your computer. So what will happen when they merge together?
When they merge together. So I can show you in a sec. I'm ready to, I'll have enough time, we're good. Basically it'll pull it, it'll say, hey, these are the same file, but the insides of each of them are different. So Git will do its best to squish them together. And like sometimes it works because you've been working on completely different parts of the file and you don't get a merge conflict. But oftentimes you'll still get a merge conflict, and it'll basically say like, I'm gonna attempt to squish these files together, and then if it can't squish them together, then it gives you a merge conflict and it lets you know with like a bunch of special characters. So like it's, when you pull it, it tries to squish them together, so you don't end up with like two of the same file, it's like attempting to squish them. That's not the technical term for it, but I like it a lot. Yeah, anything else for now? No? Yes? Wave,
So how do you manually solve the merge?
I will show you. Who's ready? Are we good? Okay, no more for now? I can't, you have to like make motion. You know the T-Rex in Jurassic Park? Okay, we're good. Okay, so here's what we'll do. So let's do a demo. So here, we're gonna pretend, can you see this? Is it big enough? Okay, I got nods, so you're locked in. So basically what we have here is, if I can get this mic to stay, we're gonna pretend these are, no, this isn't happening. Okay, we're gonna pretend these are two different repos, right? So we have left repo and we have right repo. You know, like left Twix, right Twix? Who's a left repo kind of person? You're all right repo? I see it. Who likes right repo better? All right, no one understands my question because it was a bad question. Okay, so basically what I've done here is I have initialized a repository and connected it to GitHub here. So we're going to pretend left repo is one person and right repo is another person, but they're both pushing to the same repository. So in either of them, like if I'm in left repo right now and I say git status, then I can see there are no commits yet, nothing's really gone on, but we can make stuff happen, right? So what's the first thing we should do if we want to like cause a conflict, right? Let's start with making a file. So let's make, how do I hold this and type it? This is so complicated. Okay, I'm gonna get this, it's gonna happen. Okay, any ideas for the name of the file we're gonna create? I don't know why I didn't see that coming, frankly. Go Bears? Okay, gobears.txt. Okay, so we have this new file. We can see it's there on one repo, and it's clearly not here on the other repo, right? So if we look at gobears.txt, and let's go inside, and what should we put inside? Wow. Y'all have so much spirit. Oh wait, you got it. Stanford? Okay. Yeah? We good? Alright, so if we look at it, we can see that, oh, that was a mistake. I messed up. That's not what I wanted. Okay, cat, go Bears. Okay, yeah, go Bears beat Stanford, right? So far, so good? Again, it's not over here. So we look back in left repo. What do we want to do if I want to push this to my repository? So we've made the file. What do I want to do next? Git add. Go Bears. Okay, git status. What do I see now? I see I haven't made any, oh, wait a minute. I should have asked for git status before that's fine. You know what it would have said. It would have been like, hey, here's a new file. Do you want to track it? But yeah, so basically we have changes to be committed. So this is like the staging area part, right? So what we'll do is we have our new file. It says go Bears, like beat Stanford. And then what'll happen here is if we want to push it, now that it's been staged, it's being tracked, what do we want to do? Anyway. Huh? Git commit. Okay, do we want to put a message? Trick question, yes. Okay, what do we want the message to be? Yeah, you ran out of school spirit, didn't you? You don't know what else. What do we say? Get the axe? What do we say? Do we care about the axe anymore? I feel like we've given up. Sure. Is anyone on Rallycom? I don't know what we're. Yeah. Are you on Rallycom? What do we say? What's? Oh, cool. Okay. Rallycom approved. Okay. Oh wait. No exclamation marks. Forgot about that. Okay. Git commit -m. Get the axe. No exclamation marks in your commit messages. I always forget that. Git status. So this tells me I'm ready to commit it, right? Whoa. Uh-oh. I think one sec. I think I lost my upstream. So if anyone's run into this error, let's fix it. So if I say git remote -v, no, it's right there. Hey, let's just see what happens. Okay, so if you run into this error, you can say git branch -- unset upstream. Whoops. And that should work. Why that happened, I don't know. I thought this was all working, but now we fixed it. So if anyone ran into that error, that's exactly how I solved it in the lab 2 days ago. Yeah, so where did my things go? Nothing to commit. Okay, let's try this again. Git add go bears. Git status. Oh, it's ready to get pushed. That's why. Origin master. I have a password, don't look. Okay. Oh, is the Wi-Fi? Oh, we're good. Okay, so we can look here, and we can look at my repo, and we can see it clearly says gobears.txt with beat Stanford. You can see. It's true. Get the axe. Okay, so it's now on the right, it's in the right spot, right? So now that was left repo, right? So all of you who are rooting for left repo, we're done for now. Time to root for the right repo. So here we go over here. So let's look at our git status. Nothing's really going on. So what should I do first? Git pull. Don't look. Okay, we're good. So what do I have here? I have gobears.txt. If I look inside, what does it say? Beat Stanford, life's good. If I say git show, I can see the most recent commit, get the axe. That's what we want to do. We're going to get it eventually. I don't know how many years it's been, but we're going to get it. So yeah, from here, basically, what we'll want to do is let's create a merge conflict because we want to suffer. So over here, I'm going to clear both, and both we have gobears.txt, right? So let's change one of them. So on left repo, we're going to say, let's go into Vim, let's change it. What do we want to change it to? What? I can't, wait, what was that? I thought I heard someone say, I love Stanford, which was wrong. Okay. What else can we say?
UCLA is #1.
All right, also wrong. Weird. That's so weird. Yeah, #1 public university. How do you spell? Cal, just in case you were wondering. That's us. So yeah, now we can see here, that's us, Cal, #1. And then we made a change on left repo, and so we'll go to right repo and we'll do something similar. Any ideas?
Top 2 public schools.
Okay, UCLA, you're right. Okay, so #2, yeah, let's be honest, it's down there. That would be UCLA, yeah, not us. Cool, so if we look at both, we can see some stuff. Which one do we want to push? The Cal one or the UCLA one? Cal, of course, go Bears. Okay, so what do we want to do? What's the first thing we do? Add, good, go Bears. Git commit, we put a message in, right? Go Bears. I don't know what to think of anymore. Git status, it's ready to push. Git push. I just fixed this. What's going on? Oh, that's why. Oh, you're right. Aha, don't look. All right, so let's see what's in the repo. Eventually, I love Dwinell. It's really fast Wi-Fi. Okay, so here we can see that the Cal one has been pushed. That's us, #1, not anyone else, just us is #1, public university. Go Bears. So we can see that's happened, right? Life's good. But also we want to let everyone know that, UCLA is not number 1, clearly number 2. So let's go ahead and add that. And then we'll get commit. And we'll say, go Bears, but again. And then here we'll say git push origin master. Here we go. Oh, wait a minute. This was supposed to happen. So what does it say? It says fail to push some refs. It says updates are rejected because the remote contains work that you do not have locally. This is usually caused by another repository pushing. So all of this angry message says someone tried to do stuff and you tried to do stuff and that just didn't work. So what do we want to do? It says hint, git pull. So git pull origin master. Okay, cool, life's good. Now we're fine, right? Oh wait, more angry things. So now there's a merge conflict. So now we have to fix this. So git status, things are angry, both modified. Oh no, this is not good. What should we do? So if we look at this Go Bears thing, you can see there are multiple messages and then there's a bunch of just stuff, right? So this is how Git tells us that a file has been modified by both and we have a merge conflict. So what should we do to solve the merge conflict? We have A, panic, and we have B, just delete some stuff until it works. Let's go with B. So what we'll do here is to get rid of all of this nonsense, what you want to do is it has head, and then it has all of the content that you have on, that's yours, that you've made. So this is write repo. Write repo said UCLA is number 2, right? So the head refers to whichever changes are yours. So that's ours, and then there's all of these equal signs. It's not like the equals you were learning about earlier. This is 6, 7 of them. There's no 7 equals operator in Java. Don't worry. And then it has the information from the other repository that's causing the merge conflict, and then it has this cool code that tells you the name of the commit that caused it. So which one do we want to keep? The Cal thing or the UCLA thing? Wow, good answer. Okay, so let's do that. We saw we had made some work, and then our partner made some work, and then we both tried to push it. Then we said, oh no, what's wrong? I'll pull it. And then basically write repo said, oh, I can't believe that I was just trying to talk about UCLA being number 2. Let's talk about Cal being number 1. So what we'll do is we'll delete this, delete this, delete this, and delete this, leaving none of these weird characters and stuff. And then we can save that. And at this point, we can say git status. It'll say, oh, we've made all these modifications. Git add Go Bears, and then git status. And it says, hey, you're ready to do the thing. So it's telling you you need to finish making all the changes to this merge. So we say git commit -m. Yeah, we wanted to talk about Cal Go Bears. And then we can say git status. It's ready to push. Git push origin master. And then we type in our password, we get there, DuanEl's Wi-Fi works eventually, and we click over here. We can see that, I guess that's the same. I should have chosen the other message because now you don't actually know which one it was. That's fine though. But we have pushed it, and we do have the fact that it's up to date with the master, so we know that. And then we can look over here and we say git status. On left repo, it still thinks it's up to date. So what do we want to do before we start making any other changes? We say git pull origin master, and then it goes ahead, and now we've pulled the fact that we did that merge. So now we're up to date. Did that make sense how to solve a merge conflict? Okay, before you go, I just want to let you know that there's a list of important commands here. There's some stuff about Enigma here. And then if you have any other questions, oh yeah, wait, there's a project party for Enigma on Friday. And then, yeah, thanks. What's up? Good point.